Hello, students. This is chapter 6 on optics and telescopes. The main topics that will be covered in this chapter are how a refracting telescope uses a lens to form an image, how a reflecting telescope uses a curved mirror to form an image, how a telescope's size and Earth's atmosphere limit the sharpness of a telescopic image. We cannot have as sharp or as magnified image as we want. There are limits to it put by the size of the telescope and Earth's atmosphere, how digital imaging, digital cameras have revolutionized astronomy, how telescopes are used to obtain spectra of astronomical objects, the advantages of using telescopes that detect radio waves from space, and the advantages of placing telescopes in Earth's orbit. These three are the ray diagrams that describe the three main types of telescopes. The first is called refracting, which mainly uses lens as the objective element. Then there's the reflecting telescope, where the main element is a mirror which collects the light and concentrates it into the eyepiece. And then there is the catadioptric, which is a more modern design which combines the elements of refracting as well as reflecting. This is what a refracting telescope looks like. It primarily uses lenses, and it is the first kind of telescope that was used, and Galileo was the one who directed the telescopes at the sky to look for astronomical objects. It is important to note that he didn't invent telescope. They were already made, but he was the first one who decided to look at the sky using them, and he made some improvements in them for that purpose. Then there is the reflecting telescope. This was actually invented by Newton. Refracting telescopes had some disadvantages, the biggest of them being chromatic aberration. So Newton actually thought about that issue and came up with a new design and made this reflecting telescope. This is what a reflecting telescope looks like. The most important feature of this is that the eyepiece is on the side of the optical tube, which initially looks quite strange to people who see this for the first time. And then this is a catadioptric type of telescope. One particular type of design within that is Schmidt-Cassegrain type telescope. Schmidt and Cassegrain are the names of the astronomers who developed this style, this design. And the most significant feature as we look at this is the short optical tube. In order to get a large magnification, usually the length of the optical tube has to be large. But in this, because of multiple reflections within the optical tube, the same can be achieved by a shorter optical tube rather than a larger one. And this is one of the most modern designs. Just something to note here that binoculars are like two refracting telescopes. Some mechanism inside binoculars, which is not obvious from the outside, is this reflection with poroprisms using the property of total internal reflection. So in order to understand how lenses work and mirrors work, we have to understand the principles of refraction and image formation. So some of the basic principles we have to understand is light travels in a straight line as long as it remains in the same medium. That is the material that transmits the light. So for example, if it is in air or vacuum or water, it will travel in a straight line. But as soon as it goes from one medium to another, for example, from air to water or from air to glass, at that interface, it bends. And that bending is called refraction. Refraction is the bending of light as it crosses the boundary. interface between two materials in which it travels at different speeds. Here's another thing. In the previous chapter, we said that the speed of light is constant, but the important thing is in vacuum. Speed of light is maximum and it is constant in vacuum. But when it goes into other mediums, such as water or glass or transparent plastic, then its speed is different and it is lower. And it is this difference of speeds which causes the light rays to bend in going from one medium to another. So here, there's the incident beam of light, and then there's, because the light travels slower in the water, because of that, the light bends, and that is called the refracted beam of light. When doing the analysis and understanding this theory of bending of light, we draw a line that is perpendicular to the surface, and that line is called normal. And then we note that in going from air to water, the light bends towards the normal. So how much is the bending of light? How much is the refraction? The amount of refraction is determined by two factors. One is the relative speeds of light in the two materials. For example, air and glass. So how much is the difference between the speeds? And that difference in speeds is quantified by a property called refractive index of the materials. Second is the angle between the light ray and the interface. The smaller the angle between a light ray and the interface, the more the light bends on passing through the interface. So the light doesn't always bend by a fixed amount in going from one material to another. It depends on the angle at which it strikes. And this is a property that is used to make the shape of lenses in a certain way that it can concentrate all the rays of light at one point. Image is formed when two rays of light emanating from a single point intersect again. This will become very apparent when we look at this next diagram here. So for example, in the first diagram, the person is looking at his image in a curved mirror. This curved mirror is like a magnifying mirror. So on the right is the person's face. And if we pick one point, like the tip of his nose, the light reflected off of the tip of his nose is getting reflected again by the silvered surface of the mirror. And after reflecting, those rays start to diverge. When the rays are diverging, then we can extrapolate them backwards, and the point at which they intersect, that is the point where the image of the tip of the nose is formed. And in this case, if we do this analysis to all parts of the face, we'll find that the image that is formed will be an enlarged image. Okay. This kind of image is called a virtual image. When the image is formed by extrapolating the rays, then that kind of image is called virtual image. And this is not a kind of image that you can project onto a screen. However, sometimes we can make these other kinds of images, which are called real images. So if the same person stands far away from the mirror, then these rays reflect in a different way, and they actually converge and intersect in real life. And when they intersect, then a kind of image is formed, which is called a real image. And if we put a screen there, then that image can be projected onto that screen just like a projector. So it is important to know about the difference between the real and virtual images. The lenses can focus parallel light into one point, and the point at which those rays are focused is called a focal point. The distance from the lens to the focal point is called focal length. And this is a property that is fixed for all lenses. And different lenses have different focal lengths. The smaller the focal length, the more powerful the mirror, the lens, I mean. And you must be familiar with these kinds of converging lenses, these double convex lenses, which are used as magnifying glasses. Some magnifying glasses can produce more magnification, some can produce less magnification. The ones with the shorter focal length can produce more magnification. When we use these kind of lenses in a telescope, then the image of very far off objects such as stars, that image is formed at the focal length from the lens. It is very important to know where that is, and that comes into the picture when designing a telescope. So what are the main parts of a telescope? Objective. Objective is the main light gathering element. It could be a lens or a mirror. In a refracting telescope, it is a lens. In a reflecting telescope, it is a mirror. It is also called the primary. When we look at telescopes and we try to judge their quality or their power, the size of the objective is the most important thing. As someone who is not that knowledgeable about telescopes, people usually think that it's the magnification of the telescope which is most important, but that is not the most important factor. It's the size of the objective. The bigger the objective, the more light it can collect and more sharp image it can form. And then that image can be magnified using an eyepiece. And the more sharp and bright image that has been formed, the higher the magnification can be produced, and we can still get a good image. So size of objective is most important. It is so important that many times when we talk about the telescopes, the size of the objective is the main thing that is mentioned. For example, we might say that this certain observatory has a 20H SCT, has a 20-inch SCT. That would mean that the size of the objective mirror is 20 inches, and it's a Schmidt-Cassegrain type telescope. An eyepiece, in this picture, you see this could be a single lens or a combination of lenses. This is added just beyond the focal point of the telescope's objective, and it acts as a magnifier to enlarge the image. So to understand the functioning of a telescope, the objective telescope focuses the light and forms a real image. And then the eyepiece is placed very close to the real image so that it magnifies that image and makes us see these faraway objects as magnified. In terms of eyepiece, shorter the focal length, higher the power. So in telescopes that we used in observatories, there isn't a single eyepiece, but there is a set of eyepieces which we can change according to our need. For example, if we are looking at the moon itself is a fairly big object, and we don't really need to produce a huge amount of magnification when looking at the moon. So we use eyepieces whose focal length is higher, and that means magnification is lower. So we might use an eyepiece of focal length 40 millimeters. But then if we are looking at Saturn or Jupiter, we need much more magnification. And for that higher magnification, we need a smaller focal length eyepiece. So we might go for an eyepiece with a focal length of 10 millimeters or 5 millimeters. Shorter the focal length, greater is the magnification. Now let's talk about chromatic aberration. This is a kind of an error, a weakness of refracting telescopes. And that is that at high magnifications, there are these colored fringes that appear on the boundaries of the silhouettes of objects. And overall, it produces a more fuzziness in the picture, lack of crispness, lack of sharpness. So in the upper picture of the horse, you can see those colored fringes more clearly. And then in the bottom two images, you cannot see those colored fringes that clearly, but you can definitely see that the lower picture has chromatic aberration, and it looks less sharp, less focused than the image on the top. And in that image, the chromatic aberration has been fixed. Chromatic means color, aberration means a defect. It's a defect of optical systems that results in light of different colors being focused at different places. This happens because the circumference, the outer edges of a lens, the cross section looks like a prism. And as you know, a prism can separate colors. And that is exactly why this is produced. However, it is possible to produce lenses which are achromatic or achromats. This is done by combining two or more lenses made of different kinds of glass. The powers of a telescope. There are two kinds of powers of a telescope. One is the magnifying power, and the other is the resolving power. So what is the magnifying power? The magnifying power of a telescope is how much magnification can be produced. And that is given by this formula. M is the focal length of objective over the focal length of eyepiece. So if you know if you have a telescope and you know its focal lengths, then you can calculate the magnification. For example, if the focal length of objective is, let's say, 700 millimeters, and the eyepiece we are using has a focal length of 20 millimeter. Millimeter. Then this division gives us the answer 35. And we write it like this, 35 times. That means the magnification produced will be 35 times. There's another relationship between magnification and the angular size. So this means that when we are looking at, let's say, the moon, then the angular size of the moon will look 35 times bigger. So for example, normally the angular size of the moon when we see with our naked eyes, that is half a degree. Okay. So when we will look at it with a telescope, then in the telescope, the moon will look big. And the angle that will be subtended within that will be 17.5 degrees. okay? Half times 35, that is 17.5. So that relationship is M is equal to alpha telescope over alpha I. Alpha I is the angular size that is seen with naked eyes, and alpha tel is the angular size seen by the telescope. All right. The other kind of power of a telescope is called the resolving power. The resolving power is called by the is caused by the diffraction. Diffraction is the spreading of light upon passing the edge of an object. This is related to the double slit experiment that we talked about in the previous chapter. Resolving power or resolution is the smallest angular separation detectable with an instrument. It is a measure of the instrument's ability to see detail. To understand this better, we can do a little experiment. You can stop this video and you can do this experiment yourself. I'll make two dots here, which are very close. And as you're sitting in front of your screen, you can obviously see that these two dots are two dots which are separated from each other. However, if you leave it here, you pause the video and you start walking away from your screen. Keep looking at the dots. There will come a point at which your eyes will not be able to see the two dots as separate, but they will merge into one blob. Okay. So that is the limit of your resolving power. When you're getting further and further away, the angular distance between the two dots is decreasing and decreasing and decreasing. And when that angle gets to about 1 arc minute, then those two dots dissolve into one blob and you cannot see them as separate. That means your ability to see sharpness and detail in this image is gone. However, if you see through a telescope or a binocular and the objective of the binocular or telescope is bigger, then that resolution power increases. That resolving power increases, such as a 6-inch telescope has a maximum resolving power of 1 arc second. So the resolving power can be increased by using telescopes, and the bigger the objective lens or mirror, the more the resolving power. However, there's only so much you can do by increasing the objective size because of atmospheric turbulence. Even the largest Earth-based telescopes have a practical resolving power of between 1 and 0.25 arc seconds. Operating above the Earth's atmosphere, the Hubble Space Telescope has a resolving power of 0.1 arc second or better. So this is the reason we send telescopes in space. For example, first there was Hubble Space Telescope. Now there's the Keck telescope. The purpose is to get above the Earth's atmosphere. Now, here we want to talk about why reflectors are more important than refractors. All big telescopes in observatories, they are of the reflector type, such as the Hubble Space Telescope is a reflector type. The Keck, I'm sorry, I meant to say James Webb Telescope. James Webb Space Telescope is the one in space which has replaced the job of Hubble Space Telescope, James Webb Space Telescope. Both of them are reflector type. In fact, Keck and other telescopes are also reflector type. What are the advantages of reflectors? Reflectors can be made larger and less expensively than refractors because there are fewer surfaces to grind, polish, and configure. Okay. If you're making a refractor, you have to use a lens which has two surfaces that you need to configure accurately. Whereas if you're using a mirror, then you have only one surface to worry about. Okay. There is no chromatic aberration in reflectors. Light doesn't transmit through a mirror, so imperfections in glass are not critical. Mirrors can be supported on their backs, thus minimizing shape deformations due to gravity. Lenses must be supported along their rims. Okay, I'll skip some of these. You can read about these. Best placing of big telescopes. Best viewing conditions for large telescopes are to be located on top of mountains in dry, clear climates. So you will notice that that all big, expensive telescope observatories are placed on top of mountains, and especially some areas of the Earth are more suitable where there is dry and clear climate, so that we don't have moisture and clouds in the way to distort the image. Then there are another kind of telescope, radio telescopes. Radio telescopes are like, they look like your dish antennas for TV. This was one of the largest, well, at the time, it was the largest radio telescope in the world. So the dish is actually a reflector. The radio waves that are coming, it reflects those waves and it reflects them into the detector in the center, and that it detects the radio waves and makes images and graphs out of it, from which we can learn about the properties of the astronomical objects. However, in a storm, this was destroyed, the Arecibo telescope in Puerto Rico. The images from these look like this. They are not as pretty as the images from James Webb Space Telescope or Hubble Space Telescope, but it can give us very valuable information. Here is another image that is of Andromeda, which is formed from radio waves. Here is the same image made using infrared telescope. So you can see that they look different, but each of them provides a different kind of information. Then there is interferometry. We can combine the signals received by different telescopes to form a much more detailed and sharp image that is called interferometry. Here is an example of interferometry. This is the very large, this is the VLBA, very large baseline array radio telescopes. These many telescopes are placed in a line, and they are connected in a way with interferometry that they act as a very, very huge telescope with a huge objective, and that increases the resolution, the resolving power of the telescope. So combining these different telescopes can make it look like it's a telescope, radio telescope with a very huge dish. We use other parts of the electromagnetic spectrum also for purposes of astronomy. So we have infrared telescopes, we have ultraviolet telescopes, gamma ray telescopes, X-ray telescopes, all kinds of those. Let's talk about infrared. There's the near infrared. You can place those kinds of telescopes on high dry mountain tops, such as Mauna Kea in Hawaii, because water vapor is the main absorber of infrared light. So if you put it on top of high mountains, you're above the clouds, and it can work. Far infrared is even more absorbed in the atmosphere, so we need to go even higher. There is an aeroplane, and there's a infrared telescope on the aeroplane which captures far infrared, and that project is called SOFIA project. Infrared telescopes must be cooled, so heat, IR radiation from surroundings does not mask signals received from space. Anything that is hot or even warm emits infrared light, even human bodies. So if you're trying to detect the infrared light from stars and planets, it's like you're surrounded by bulbs emitting light, infrared light. So in order to reduce that effect, the infrared telescopes must be cooled. Ozone is the chief absorber of wavelengths shorter than about 400 nanometers. So ultraviolet X-rays and gamma rays, these are all stopped by ozone. And that's why we don't have any of these kinds of telescopes on Earth. All of these UV, X-ray, and gamma ray telescopes are in space. And Hubble Space Telescope is mainly an optical telescope with 2.4 meter primary mirror, but it is designed to observe across the spectrum from near infrared to near ultraviolet. And now James Webb Space Telescope has been launched and put in space, and now it is the successor to Hubble Space Telescope. So with that, we get to the end of this chapter. This is an image of the Hubble Space Telescope.